Hello everyone. So today we are going to start with a new module. This is module 5, mean flow equations. So in this module we are going to be dealing with the Reynolds equations, obviously for continuity, momentum. Then we are going to be dealing with Reynolds stresses, the closure problem, we're going to discuss that in detail, the anisotropy in turbulence, how the irrotational motion comes. We'll talk about symmetries, just briefly go over the mean scalar equation, and discuss one of the most important hypotheses for turbulence modeling, which is the gradient diffusion hypothesis, coming from the turbulent viscosity hypothesis, and what its implications are. So we're going to be dealing with a lot of math here where you mostly looking at the equations involved, and mainly the mean flow equations. So the content in this module comes from Pope's book, Pope's Turbulent Flows book as well. So let's start with the continuity equation, and here what we are going to do is we are going to derive the Reynolds equations for the continuity and momentum. Now if you look at a turbulent velocity field, we know it is a vector. It has three components, u1, u2, u3. So I have my u as u1, u2, u3. These are all instantaneous. And x, the position vector, as x1, x2, and x3. And since it depends on time as well, it's actually technically a 4D variable. The Reynolds equation is obtained by taking an average of the governing equations, meaning you take the average of the continuity equation and the average of the momentum equation. Average gives you the mean. So the governing equations for the mean are the Reynolds equations. So you have a mean velocity, let's call that mean of u, which is also a vector because you will have a mean of u1, mean of u2, and a mean of u3. So u1 mean, u2 mean, and u3 mean. This is averaged over a period of time. So your Reynolds decomposition decomposes your instantaneous velocity into mean and fluctuation. And so you can write the fluctuation as instantaneous minus the mean. This is the Reynolds decomposition. So as an exercise, if I just take the average of this particular Reynolds decomposition equation. So what I have is, I have u is equal to u minus mean of u, isn't it? Now I take the average on both sides. What I get is average of the fluctuation of u is the average of u minus average of u. So if you take an average of u, you get the same thing. It doesn't change. So the average of u is the average of u. So on the right hand side what I have is average of u is average of u is average of u. So this becomes equal to 0. So what have we learned from this? The mean of the fluctuation is equal to 0. The mean of fluctuating velocity is equal to 0. Now, going back, once you do that, now you know that the mean of the fluctuating velocity is 0. Now let's start with the continuity equation. What we know is that the continuity equation is del dot u, isn't it? Del dot u, and you decompose the u, because that's your instantaneous, into u mean plus fluctuation. That has to be equal to 0 according to continuity. Now you take an average of that. So I'm going to go back to that page and start doing now. If I have del dot u, which is equal to del dot u mean plus fluctuation, isn't it? This is equal to 0. So your del dot gets distributed into the brackets, and then you have del dot u mean plus del dot u is equal to 0. Now I take an averaging on both sides. Then what I get is average of del dot u is equal to, I take an average of del dot average of u. So that just becomes del dot average of u itself plus del dot average of fluctuating velocity. This has to be equal to 0. We know it according to continuity. So essentially what you're saying is now this one here is equal to 0 because the mean of the fluctuating velocity is equal to 0. We already saw that. So that means the average of the continuity equation is equal to the divergence of the mean of the velocity, which is equal to 0. Which means this is telling me that if the divergence of the velocity is equal to 0, the divergence of the mean of the velocity is equal to 0, isn't it? From here, the divergence of the mean of the velocity is equal to 0, which means the divergence of the fluctuating velocity has to be equal to 0. By the way, all of these are vectors. All of these are vectors. So just so that we are clear, we are taking a divergence. It has to be a vector. Otherwise, divergence doesn't make any sense, isn't it? So just so that we are clear. So then what you have is del dot u is equal to 0. Also, what we know is that del dot the average of u is equal to 0. Obviously, because the average of fluctuating velocity is 0 itself. So the divergence of that is going to be 0. But what now we know is that the del dot, the fluctuating velocity, is the divergence of the fluctuating velocity is also 0. So capital U follows continuity, mean of U follows continuity, and the fluctuating U also follows continuity. All of these satisfy continuity. Separately, the instantaneous velocity obviously satisfies continuity. That is what we started with. But now we know that the mean velocity also satisfies continuity and the fluctuating velocity also satisfies continuity. So satisfies continuity. That's what we learned from this. So that's what we have here. Del dot u is equal to 0. Del dot capital U is equal to 0. Del dot mean of u is equal to 0. And del dot fluctuating velocity is also, mean of the fluctuating velocity is also 0. Now that continuity is done, let's go into momentum. Now the momentum equation has one additional complication, the nonlinear convective term. So taking the average is not as straightforward as what we saw for the continuity. So as a preview for that, let's start by taking the mean of the substantial derivative, because we know that the left hand side of the momentum equation has the substantial derivative there. So let's start by taking the mean of the substantial derivative. So my substantial derivative definition is this one. And since I'm dealing with uj, I'm writing the substantial derivative in terms of uj. So duj dt on the left hand side is del uj del t plus del xi ui uj, isn't it? That's the definition. Now, when we earlier wrote the substantial derivative, we always wrote this thing as d dt. So d dt of any variable is del of that variable del t plus it becomes u dot del. But since we are using the continuity in there, we are writing this as del xi of uj. If you see here, this component, this can be written as ui del I uj plus uj del j uj. This term goes to 0 because of continuity. So this essentially comes out to be del t uj plus ui del I uj. That's another way of writing it. Or we could also write it as what is shown here in the slide. Del t of uj plus del xi of ui uj. Now what you do is you take a mean of that. So once you take a mean of that, what you have is del t of uj plus del xi of mean of ui uj. Del xi of mean of ui uj. So then you will substitute the Reynolds decomposition of these components. So ui uj mean becomes ui plus ui, as in mean ui plus ui, multiplied by uj mean plus uj. So then you will have ui uj, as in ui mean uj mean, plus ui mean uj plus uj mean ui plus ui uj. Now, and you are taking an average of all of that. This is obtained by just multiplying this through, using the distributive property, multiplying this through, and then you take the mean of all of that. Then what happens? So just so that we are clear, if I have ui uj like we had previously, ui uj, and then I take the mean of that, what I end up getting is ui uj, like this, ui mean, uj mean. This is 0, isn't it? Mean of the fluctuating component is 0. So that's what ends up happening here. This two terms goes to 0. Because when you take an average of that, those two terms go to 0. What you're left with is ui mean, uj mean plus ui uj mean. This is the Reynolds stress. This is the product of the two means, two components, ui uj. So that is what you end up substituting in the mean of the substantial derivative. duj dt is del t of uj and del xi of these two components that you end up substituting here. Before doing all that, I am going to define a mean substantial derivative. So this is not the same as the mean of the entire substantial derivative. I am defining a mean substantial derivative as, so a new way of defining a substantial derivative. So that would be del t plus u mean dot del. So that means a mean substantial derivative of something is del t of that sum quantity plus the mean dot del of that sum quantity. All right. So now when I take the mean of the substantial derivative like what is shown here, and I'm going to go back and sort of derive this. So now when I take the mean of the substantial derivative, duj dt, mean of that is del t of uj plus del xi, and again I am using the mean substantial derivative equation, right? This one right here, which is substituted with this part here. And what I end up having is del xi of, see, ui uj mean, right? Ui mean, uj mean, and then also del xi of the Reynolds stresses, ui uj mean. This is what I have. So this ends up being, so I'm going to simplify my notation and just write it as del t of uj instead of writing it as del t. So I'm writing it as del t uj. You understand that it is a time derivative. And then what I'll end up having here is ui del I uj plus uj del I ui plus del I Reynolds stresses, ui uj, isn't it? Now this term goes to 0 because the mean velocity satisfies continuity. Then what you end up having is del t uj plus what you end up having is ui del I uj. I'm sorry, this is mean, right? This is mean. del I uj mean plus del I ui uj Reynolds stresses. This right here is the mean substantial derivative of uj. So your mean of the substantial derivative is equal to mean substantial derivative of uj plus the Reynolds stresses. Derivative of that, of course. That's what we end up getting if you have it like this. So going back to this slide, what you end up having is you are now defining the mean substantial derivative. That is how I got this equation. Now you substitute that into the momentum equation, then your left hand side is entirely mean substantial derivative is equal to the viscous term, the Reynolds stresses term coming from here, and then the pressure gradient term minus 1 over rho del xj of the mean of P. So what we have tried to do by doing all this math is to try and express the Reynolds equations of momentum in a similar way as the original momentum equation. So you have a substantial derivative on the left, except this is a mean substantial derivative, so there's more to it. The mean substantial derivative is equal to viscous term plus the pressure gradient term. All that is very similar to the original momentum equation. And then you have a Reynolds stresses term minus a Reynolds stresses term. The only difference, if you think about it, the only difference between this Reynolds equation and the Navier-Stokes equations is the presence of this Reynolds stress term. Reynolds stress term, RST. And that is a big difference. Now we are not done. We should also now think about the Poisson's equation, because when you're taking an averaging, you would have to take an average of that as well. So just like you have a velocity that is fluctuating, you also have a pressure that is fluctuating. So you'll have a mean pressure and a fluctuating pressure. But here what we are doing is we are going to be taking the divergence of the momentum equation to obtain the Reynolds form of the Poisson's equation. Just like earlier, we got the Poisson's equation by taking the divergence of the Reynolds equation. We got the Poisson's equation by taking a divergence of the Navier-Stokes equation. Here also, we will take the Reynolds form of the Poisson's equation, the mean form of the Poisson's equation, by taking a divergence of the Reynolds equation. So here is how we are going to do it. We are going to be writing this out. So what I have is del uj, so del t uj plus ui mean del I uj, isn't it? This is my Reynolds equation. And then I have minus 1 over rho del jp, mean p, plus I have the viscous term, nu del squared and nu del squared uj, isn't it? Minus del I, the Reynolds stresses term, ui uj mean. Now what I do is I take a divergence of that. So del j of the whole thing. The first term ends up becoming 0 because I'm taking del j uj, plus the second term, what I'll end up having is I will have del j ui del I uj, and then here for pressure what I'll end up having is minus 1 over rho del j p, plus the viscous term becomes 0 because I'll have again a del j uj, and then here again what I'll have is I'll have del I del j ui uj, Reynolds stresses. So that is what I end up having. So then if I write this in, this becomes del j becomes minus 1 over rho del squared p, isn't it? And this is actually mean p, This is actually mean P. And then I will have minus del squared del xi del xj of the Reynolds stresses. And on the left hand side, I'll have del ui del xj and del uj mean del xi. This is exactly what I am going to get here. This is the Poisson's equation, the equation for the mean pressure field obtained by taking a divergence of the Reynolds equations. So what you end up having is the Laplacian of the mean of pressure is this term here plus this additional term that arises because of turbulence. It's like the second derivative of the Reynolds stresses. So that's the additional term that happens. So I hope this is clear. So the Reynolds stresses play a crucial role in the mean velocity field. If the Reynolds stresses were 0, then u and u mean would be identical, isn't it? Because if you think about it, this equation here, if this RST term becomes equal to 0, there's no difference between this and the Navier-Stokes equations. Then whatever you end up getting by solving the Navier-Stokes equations, you would get the exact same equation by a solution by solving this equation if the Reynolds stresses were 0. And the Reynolds stresses are 0 for laminar flow. For turbulent flow, they are non-zero. So finally, when you write your Reynolds equations, you can write it in this form. The viscous term can be split into this because, as you know, this will end up, one of these terms will end up being 0 because of the continuity, and you will end up having a second derivative like a diffusion term, viscous diffusion term. But otherwise, this term is exactly what I had written earlier. It is the Reynolds equations. You have the mean pressure. We have put in the Kronecker delta to indicate the fact that you only have a derivative of pressure with respect to one component in each of the three equations. So that's the reason mathematically, in order to make it appropriate, you're putting the Kronecker delta there. And then you have this Reynolds stress term. This is the additional term that arises because of turbulent flow. So now the left hand side is sort of like an acceleration, right? d dt, it's the mean substantial derivative of the velocity. It's a derivative of velocity, which means it is like an acceleration. That is equal to, you have the three components, the three stresses that are making up. The Reynolds stresses, the isotropic pressure stress, the normal stress, and then the viscous stress. So you have three components that makes up the viscous stress, the isotropic stress, and the apparent stress coming from the fluctuating velocity field, which is the Reynolds stress. So the viscous stress comes from the molecular level. It stems from the momentum transfer at the molecular level, whereas the Reynolds stress stems from the momentum transfer of the fluctuating level, fluctuating velocity field. So this part here, and this comes, we have discussed this a lot when we discussed laminar and turbulent flow, right? You have this turbulent mixing which is due to the fluctuating velocity field, velocity gradient, which is a macro property, whereas the viscous mixing is a micro property. It comes from the molecular level. So that is what we mean by this statement. The viscous stress ultimately stems from the momentum transfer at the molecular level, whereas the Reynolds stress stems from momentum transfer due to the fluctuating velocity field. So that is at a macro level. Now, going further, let's say we want to evaluate the rate of gain of momentum within a fixed control volume. So the rate of gain of momentum can be written like this. So using a control volume analysis, you can just write it as rho u minus u dot n dA. And keep in mind, the momentum per unit volume is rho u, and the volume flow rate is minus u dot n. Now, if I take the mean of that, this is essentially the ui uj. It is actually the ui uj component. So if I take the mean of this equation here and take only the j component of that, so take the mean of the j component, what I end up having is ui uj mean plus this Reynolds stresses in the same way as I had derived earlier. Now this is I wrote it as an area integral. I can write it as a volume integral by using the divergence theorem. So then I end up having del xi of ui uj and ui uj ni dv. This is exactly what you saw in the Reynolds equations. So the mean of the j component of the gain in momentum is given by del xi ui uj plus ui uj, the Reynolds stresses. From here to here, you obtain it through the divergence theorem. Huh? So that's what you end up having for the mean of the j component, where you will have del xi of ui uj and ui uj mean, the Reynolds stresses. So what we are only trying to show is the rate of gain of momentum comes from two components. One is the mean component here, and the other one is due to the Reynolds stresses as well. So that is what we mean by it arises from the mean momentum flux due to the fluctuating velocity at the boundary. That is where the additional gain in momentum comes from. In a laminar flow, this wouldn't be there. You would only have the first component. So we are looking at it from another perspective. Earlier, when we saw the Reynolds equations, we realized that except for the Reynolds stress term, everything is similar to what we have in a laminar flow. So this is the additional crucial difference that comes when you have a turbulent flow. In the same way, when we look at the gain in momentum, the contribution is coming from the momentum flux due to the fluctuating velocity, the Reynolds stress term. So here in today's class, what we have done is we derived the Reynolds equations both for continuity and momentum and looked at the physical significance of this additional term that comes about because of the turbulent flow. In the next class, we'll delve deeper into these equations and look at what the closure problem is, what anisotropy is, and what symmetries we have to deal with. Thank you.